So we're in the chapter that deals with reacting mixtures and especially combustion. And we've covered the reaction equation and balancing it. And then we need to move into conservation of energy in the first law. This problem, let's take a look at this problem. So hexane C6H14 burns with dry air to give products with a dry molar analysis of, so these are key words, dry molar analysis of, and then 10.7% CO2, 5.4% O2, and 83.9% N2. And it asked, for the first part is, give me the balanced reaction equation. So start with the hexane, C6H14, and we're going to get the oxygen from air. Okay? And so we leave a space in front, and we're going to be determining that stoichiometric coefficient in our equation. And so we'll assume complete, so that those are on the left-hand side, the reactants, and the products on the right-hand side. From the dry molar analysis, we know that it's 0.107 CO2 and 0.054 O2 and 0.839 N2 multiplied by some unknown coefficient. That gives me the right proportion of the dry molar analysis. And then what was not accounted for is how much H2O. So basically we have three coefficients to determine, true? So let's take a look at this. If you do a carbon balance, maybe I'll try and tuck it up here, a C balance. If you do a carbon balance, how many are on the left-hand side? 6. And so what do we have on the right-hand side? Some unknown coefficient, we can call that A, times 0.107 times 1. Any other place carbon? No. And so we can determine that A, true? And so we'll determine the A to be 56.07. 56.07. All right. Now, let's take a look at a hydrogen balance. We have a carbon balance, then a hydrogen balance, true? How many hydrogens on the left-hand side? 14. How many hydrogens over here? So we determine what's in front of the H2O. Can you see what the coefficient A is? 2A in front of the H2O? 7? True? So we solve for that coefficient in front of the H2O. And then the next balance would be an oxygen balance. So if you do an oxygen balance, I have 2 times, and I'm just going to continue to reuse the letter A. 2 times A is equal to 56.07 times 0.107 times 2 plus, this is a square bracket, 0.054 times 2, close that bracket, add 7. True? Did I do the oxygen right? So you're accounting for the contribution, the contribution, the contribution. I'm sorry, it's a long equation, but it wraps around this bracket, closes this bracket. That's a 2. Okay. And if you solve for it, you find that you need 12.53. So we'll just put 12.53. Last balance, do a nitrogen balance. Let me just put it up here. We have 12.53 times 3.76 times 2. Is that equal to 56.07 times 0.839 times 2. And the answer is close enough. It's good to right at 3 digits, not 4 and 5 and 6 digits, but you know, it's because these numbers have been truncated, it's close enough. So the nitrogen balance is a check. So there is the answer to part A. We can go ahead and box it. Guess I should get rid of this underlining here. And there you go. Now, what is the percent theoretical error? Well, we should get a balanced equation with just normal combustion, 100% combustion of this hexane fuel. So C6H14 plus O2 plus 3.76 N2 goes to CO2. We can do the carbon right away because carbon only occurs in front of the CO2 and in the fuel. So that's 6 plus H2O. Do the hydrogen balance right away. 7 plus, do the oxygen going backwards. So that's 12 plus 7 is at 19. Then 19 divided by 2 will be the coefficient in front of the air. And to finish it out, balance the nitrogen, 19 over 2, 3.76 N2. So there it is. That's would be the amount of, this would be 100% theoretical error. Okay. But for the original problem, what is the percent of theoretical error? Well, we're going to have the number of moles of air is equal to 12.53 times 4.76. True? That's how many moles of air you actually have per mole of fuel. How about if it's 100% theoretical? How many do we have? 19 over 2 times 4.76. True? So if you take that ratio, the percent theoretical error, there's no nice symbol for that, so I just write it out. Percent theoretical error is equal to the ratio of 12.53 divided by 19 over 2. You see that? So how much air actually was used versus if it would have been 100% theoretical error, which was 19 over 2. Oh, you could put the 4.76 on both sides. 4.76. But they cancel, right? Because they're in both here. And so when I do that ratio, we calculate that it's 132% theoretical error. Or just leave it like this. Theoretical error is 132%.
Where did you get the number 2?
I had to balance it for 100% theoretical error. And then really what I'm doing is I'm comparing this to this. All right. So 12.53 divided by 19 over 2 gives us that it's 132% theoretical error. Part C asks, what is the air to fuel ratio on a mass basis? So air to fuel, that's the mass of air. So we do the number of moles of air times the molar mass of air divided by the mass of fuel, the number of moles of fuel times the molar mass of the fuel. So the number of moles of air, 12.53 times 4.76, true, times 29 or 28.97 kilograms per kilomole for air, the molar mass. Now we had 1 mole of fuel, and we have to get the molar mass of fuel. I look up hexane. I don't see it anywhere in the appendix, but I can calculate it close enough, right? Every carbon is worth 12, and every hydrogen is worth 1. So 12 times 6 plus the 14 gives me 86. And so the air to fuel 20.1, meaning I need 20.1 kilograms of air per kilogram of fuel in the combustion chamber. And then what is the dew point temperature of the combustion products in degrees C, assuming it's at 1 bar? So the way you do it is calculate the mole fraction of vapor in the products. The mole fraction of vapor in the products would be the 7 moles of water, that's how many moles of water, divided by the total number of moles of everything, and you can calculate that by doing 56.07 times 1.07. That'll give you the number of moles of CO2. Add that. That'll be the number of moles of CO2 and O2. The number of moles of CO2, O2, and N2 added with the 7 from the vapor. So that gives me the total, in the denominator, total number of moles or kilomoles. So the mole fraction of vapor is right at 11.1%. So the vapor pressure is the mole fraction of the vapor times the atmospheric pressure. Atmospheric pressure is 1 bar, and so it's 0.111 bar. And then we do interpolation in the table to find the temperature dew point. It's around 48 degrees C. So around 48 degrees C. If the products go below that, you'll have water condensing. If the product temperature is above that, then all the water can be in the vapor state. Make sense? Yeah, I have to count up the total number of moles over here in the products. Right? So that's the way I did it. And then I have a mole fraction is how many of them are vapor? 7 out of all of those are vapor. Pardon? Well, okay, if you want to make this computation right here, and then I think you'll find that that is around 6 moles of carbon dioxide. Then make this product here, and you'll find it's like 3.03 moles of O2. And then if you make this product here, you find that it's around 47.05 moles of nitrogen. And then add that to the 7 moles of water. All right. Why you mentioned the reaction side? Because all of these are consumed. It's 100% from the reactants to the products. Now, if we would have said some of this hexane is not burned, we would have put it over on the product side. We would have put some unburned hexane, uncombusted hexane in the product side. Let's introduce our conservation of energy. It's probably good to have a system and talk about it. The book talks about if I bring in carbon, actually a solid, and I bring in oxygen in a gas phase into a reactor, and the product will be CO2. Okay? We can do this problem as a baseline. Or we can do this problem where you're bringing in methane, CH4, and you're bringing in air, which is O2 plus 3.76 N2, some amount, and you'll come out with CO2 and H2O, true, and N2. This is a little harder because it's more tedious, but this is almost too straightforward or too simple. Which one do you want to do? The CO2, making CO2 out of carbon and oxygen, or burn methane with air to make water, vapor, and nitrogen goes along for the ride. Methane? Okay, so we'll do the methane example. And so the conservation of energy for this, remember this is our fuel, this is our air, both of these are our inputs, our reactants. And we have a bunch of products. Now, it's a little bit of a misnomer. Let me point out, there's N2 in the reactants and there's N2 in the products. So you have to be careful that sometimes in a balance equation, N2, oh, that means it's coming in the reactants. And this N2 is the products. All right? All right. Also, if you have incomplete combustion, you could have some CH4 in the products. It just gets nastier, okay? But whatever's in the products, you'd have to account for. Or if you had, too much fuel. Did I say incomplete combustion? If you had incomplete combustion, maybe you'd have carbon monoxide in the products. You just have to do all the balancing. You have to do all the bookkeeping to keep it all straight. All right. But let's assume you're going to have to know that this comes in at some temperature and pressure. Almost always they come in at 25 degrees C and 1 atm. Almost always. The standard input. Methane at that temperature and pressure is in the gas phase. Oxygen, gas phase. Nitrogen, gas phase. All right. Then they come out. They can come out hot. They can come out lower temperature. You don't know the temperature. A lot of times we compute that. If this is insulated and burning methane is an exothermic reaction, it'll come out at the highest temperature of the products. That highest temperature is called the adiabatic flame temperature. Otherwise, there will be some heat transfer between the reactor and the surroundings. The combustor and the surroundings, true? And because we're going to do a control volume right around the reactor, we would designate that this Q, the direction, traditional thermodynamic direction for that heat transfer is positive in. We'll stay with it. The book is consistent, staying with its positive in, even though we do a lot of combustion calculations and they're exothermic. And when you calculate Q dot, it's negative. You're going to see a lot of negative quantities in this chapter. Why? That's the reason. Positive in for the heat transfer. So you'll see a lot of negative entities. All right. So let's write down our energy balance. This is Q dot in is equal to the sum of the mass flow rates and the enthalpies of each and all of those products going out minus the sum, the mass flow rate and enthalpies of each of those reactants. There's no work, no shaft power, anything like that, so I didn't write it. It's steady state, no accumulation, depletion, I didn't write that term. No negligible changes in kinetic and potential energy, so I didn't write those terms. True? But this is the first law. We have heat transfer in, and we have the products going out with their enthalpy and the reactants going in with their enthalpy. Often we don't like to work in mass flow rates, we like to work in molar flow rates. So we put an H bar for each of those products and a sum over all the reactants, N dot H bar. What's the difference between H and H bar? One is kilojoules per kilogram. H bar is kilojoules per kilomole. True? What is the difference between M dot and N dot? Mass flow rate, kilograms per second. N dot, molar flow rate, kilomoles per second. So the next step is we say, well, normalize this equation by dividing by N dot of the fuel. N dot of the fuel, N dot of the fuel. And what you get is you get this ratio. It's how many kilojoules of heat transfer from the surroundings into the control volume per kilomole of fuel coming in to the reactor. Then you have the sum over the products, and they put N without a dot on it, H bar. So what is N without a dot on it? It's the number of moles of that species, of whatever product it is, per mole of fuel. It's really a stoichiometric coefficient in our balanced reaction equation, especially if you leave 1 in front of the fuel. All right?
That's not the same as the molar percentage?
No, there would be those stoichiometric coefficients because it's the N is equal to N dot of whatever species of the product divided by N dot of the fuel. So this is how many kilomoles of the fuel per second or hour or whatever flow rate. And then this would be something like how many kilomoles of oxygen per second. See, so it's a ratio of whatever product you have coming in to the molar flow rate of the fuel per fuel, minus then the sum of the reactants NH bar. So those N's come from our balanced reaction equation. All right. Now, let's go ahead and write our balanced reaction equation for methane. CH4 plus, can I do it with just pure air oxygen, or should I do it with the nitrogen as well? Which one? Do it with the N or not with the N? All right, fine. We'll leave the N. 3.76 N. It just makes it longer. How many CO2s do I have to have? 1. How many H2Os? Balance the hydrogen. How many H2Os? 2. You're getting better. Count up the oxygen on the right-hand side. 1, 2, 3, 4. 4 over 2. And then we have 2 times 3.76 N2. Did I balance that equation correctly? Good. One thing is the product of 2 times 3.76, because we'll have to write that a few times, we can just write it once, and it's 7.52. That's that product. 2 times 3.76, 7.52. All right? So now, so what we have is Q dot over N dot of the fuel is equal to, I'm going to write it like this. For each of the products, let's write the product CO2 first. So we'll put N H bar CO2 plus N H bar of the next product, H2O, plus N H bar N2. And I'm going to put N2P because it's so confusing. It's N2 of the products. And then minus NH bar of CH4 minus NH bar O2 minus NH bar N2 reactants. You see that? All right.
So since the nitrogen stays the same in the reactants and the products, do you have to really skip that?
You could if they came out and in at the same temperature. If they came in at the same temperature they went out, you could cancel them. If it comes out hot, you can't. All right? Yeah. So, okay, now these ends, you can get these ends right now. That's a 1, isn't it, in front of the CO2? What is the in front of the H2O? 2. What is it in front of this nitrogen in the products? 7.52, which is the same as the nitrogen in the reactant, 7.52. The amount of nitrogen, it doesn't pair up with anything and change, like oxygen goes to CO2 and water, and it stays N2. It doesn't really react, it just goes along. And then this is 1, and this is 2. Do you see all the N's? Now the hard part, the H bars. And so a lot of people have studied this notion of understanding combustion or chemical reactions, be they exothermic, endothermic, and they said we'll put everything on the same energy scale with the same datum point, and they had to pick some datum points, just like they picked where you measure energy, internal energy and enthalpy for water, right? They picked the triple point, and they picked the internal energy of saturated liquid to be 0. They just picked it. How about when they went to refrigerant? They said, okay, for refrigerants like R22, R134A, we pick negative 40 degrees, saturated liquid's enthalpy is 0, if my memory is correct. They just picked it. Well, what they did here is they looked out and they said, you know, what's stable at 25 degrees C and 1 atm? Oxygen's stable. Nitrogen's stable. There's some other things like carbon are stable. So what they did was they developed an equation where each one of these H's is an enthalpy of formation from some basic building blocks in chemistry, like stable oxygen, stable nitrogen, stable carbon at 25 C and 1 atm, and any deviation from that condition. So the CO2, it could come out really hot compared to 298 Kelvin or 25 degrees C. So this is H bar of the CO2 at the exit temperature of the products, minus H bar of 298, which is our reference. All this is for CO2. Okay, so we have a 1 there, plus 2 times the enthalpy of formation for the water, plus that molar enthalpy at whatever temperature of the products that the water's at, minus the enthalpy of formation at 298 for the water, plus 7.52 times the enthalpy of formation of the nitrogen, plus if it comes out at a different temperature than 298, that term is non-zero, that difference is non-zero. So that's the nitrogen in the products, minus 1 enthalpy of formation for the methane, plus, and I'm going to leave it like this for the methane, CH4, because what you do is you quickly realize the book gives you some ability to calculate these delta H's. Oh, it's at 500 Kelvin versus 298. But they give you no information or very little information, make it very hard for you to calculate that the fuel would come in anything but standard conditions. You find, give me the difference in enthalpy of propane between 500 Kelvin and 298 Kelvin. Yes, you can do it. It's a lot of work. Okay? So often, just put this in the back of your mind. If it comes in at standard conditions, that delta H on the fuel is 0. All right. Minus, let's continue to work, 2 times the enthalpy of formation for the oxygen plus any delta H bar for the oxygen. And you know what? I said that it's all going to come in at 25 degrees C, 1 atm, so that's 0 there too. Although if it came in hot, you could put that right there. That's where you would fix it. And then you have minus 7.52 enthalpy formation plus, and this is, let me write it like this, enthalpy temperature reactants minus enthalpy 298. N2 of the reactants. Again, we assume this temperature of the reactants is 298, hence that delta H is 0. All right. Where do I get the enthalpy of formation? Well, I'm glad other smart people have studied this, experimentally measured it, tabulated it, put it in the book for you. So let's jump to this table, table A25. Different books will have it different places, but you can typically find a table of thermochemical properties of selected substances notice that temperature, 25 degrees C and 1 atm, standard conditions. So carbon, solid carbon, like coal, solid carbon. Nitrogen in the gas state, oxygen in the gas state. Here is carbon monoxide, carbon dioxide in the gas state. Water can be in the gas or in the liquid state, so they have that parenthesis L for liquid. And then down here, I just skipped a bunch, but methane in the gas state. Notice they give us the molar mass. Then this column, it's our enthalpy of formation. It's H bar naught subscript F. It's the enthalpy form. Look at the units. Kilojoules per kilomole. It's just like H bar. All right. And notice a lot of negative numbers. A lot of negative numbers because they're hydrocarbon type fuels and you get exothermic reactions, and that's why you have a lot of negative numbers. Okay. Why the subscript F? Have I seen an HF before? Yeah, that would be for saturated liquid. They had to reuse H and they had to reuse the subscript F for something different than the enthalpy of saturated liquid. Just, that's what you find, true? How many times have you seen beta defined or theta defined or whatever? X defined. X is reused so many times. So here it is. Don't be confused. This is not the enthalpy of saturated liquid. It's the enthalpy of formation on a molar basis. True? And what's this naught imply? Standard temperature, pressure, standard conditions. Okay. So that's, I mean, this is a lot of things to note. It's H bar F naught. Okay. Now the other thing is some of these values, like diatomic oxygen right here, what is its enthalpy of formation? 0. It indicates that that's a stable element. That's one of their reference points that they started with. That's set to 0 for the oxygen. What about if they would have had monoatomic oxygen in the gaseous state? First of all, oxygen doesn't like to be the monoatomic. It wants to react, and so you could probably find somewhere else its enthalpy of formation, and it would not be 0. It would not be 0. Okay, nitrogen also is very stable. A diatomic nitrogen, and its enthalpy of formation is 0. And then solid carbon is set to 0. They picked it. So they picked some of these things to be 0. And then other things are built up from the combination of carbon and oxygen to get carbon monoxide, or the combination of carbon and oxygen to get carbon dioxide. Notice carbon monoxide and carbon dioxide. Which one do you not want to breathe because you can't breathe, then it's an asphyxiant, right? Carbon monoxide puts you to sleep and possibly death. Carbon dioxide, no problem. If you get a high concentration of carbon dioxide, you get drowsy and you may get a headache. And that's really high, like 5,000 ppm or 2,000 ppm. Depends how long you're exposed to it, and some people are more sensitive. Like some people are sensitive to the oak pollen in the air, and some people aren't. Some people are more sensitive to high levels of carbon dioxide, some people aren't, okay? But you typically get some sort of headache, nauseous, drowsiness, right? So they, so this one is incomplete combustion. This one's more complete combustion. And now you can take the CO and add to it 1/2 O2s, and guess what? It completes the combustion and it's more exothermic. You get more energy release. That's why this number is not as big of a magnitude as this one. Because if you just had C and you went with 1/2 O2, you would produce CO, carbon monoxide. You could then take that output with 1/2 O2 and get carbon dioxide. It'd be some heat release from this reaction, heat release from that reaction. The sum is the heat release going all the way to carbon dioxide. So you can look at the relative magnitudes of these numbers sometimes and it makes sense. Did I point also out that water can be in the gaseous state or liquid state? So you have to be careful there, okay? And the difference between those two values, HFG. HFG. Oh, it's on a molar basis? You have to use the molar mass to make it work. Let's jump back now that we have these enthalpies of formation and try to continue on with this problem. So in the interest of space, I'm just going to try and tuck it in here. The enthalpy of formation of the carbon dioxide was negative 393,520 kilojoules per kilomole. Let me go back and look at that. I had to get this right here. Right? That's the enthalpy of formation of the carbon dioxide. Then the enthalpy of water, and this is in the vapor state. I like to put a V or a G there. It's water vapor. That enthalpy of formation is negative 241,820 kilojoules per kilomole. And then the enthalpy of formation of nitrogen, 0. It's stable. Enthalpy of formation of nitrogen here is stable, 0. And the enthalpy of formation of the oxygen is 0. And the enthalpy of formation of the methane, we had to look that up, and the methane's was negative 74,850. Just come back. There it is. So we had to get this, and this one. Those three enthalpies of formation to do an energy balance. So we come in, if this air and the fuel were both at 25 C, 1 atm, these deltas are 0, 0, 0. And we can finish this if we knew the temperature of the products. The temperature of the products. Well, I made up this problem where we have methane at 25 C, 1 atm enters a furnace operating steady state, burns completely with 100% theoretical air that also enters at 25 C, 1 atm. And the products of combustion exit at 25 C. What? How can you have the products of combustion enter at that same temperature? And you know it's exothermic. Heat transfer. And so we don't have a large Q dot N, we have a large negative Q dot N, meaning there's a lot of heat transfer out of that combustion chamber. Okay, so this problem calculates what is sort of the max, largest magnitude of heat transfer out, where the products would come out at 25 degrees C, the reactants come in at 25 degrees C. All right? So it says determine the heat transfer from the furnace to the surroundings in units of kilojoules per kilomole of methane. We can come back and do this problem now. So that products come out at 25, they come out at 25, they come out at 25. See all that? So all of these now, let me just strike this again. This one, and this one, because the temperature of the product is all 298 Kelvin, 25 degrees C or standard temperature. And we then can calculate Q dot over N dot F, and it's negative 593,400 kilojoules per kilomole of CH4. So I know the sign is correct in that it's not into the box, but it's out of the box, out of the reactor, but it's a large magnitude. All right? Let's say we changed the problem up, and this is the same wording, but the products of combustion exit at 900 Kelvin. Now calculate the heat transfer. Jump back to the problem here. Do you think we'll get something? I know that negative sign is always something to struggle with, but the magnitude of it will be smaller than 593,400. True? If you go back and solve this problem, you'll have to change right here. You'll have to change right there. You'll have to change right there. All right? And when you do that, in the interest of time, I'll just give you the answer that I don't have written down. Sorry. I didn't write it down. Or maybe this is the answer for the 900. Oh yeah, that's right. 802,310 kilojoules per kilomole CH4. This was for the temperature of the products to be 298. This is the temperature of the products to be 900. Sorry about that. So it's negative 800 versus negative 593,000. I'm going to go ahead and stop.